Okay, let's get started. Here we go. Okay, so I let you know late about making a PDF out of your homework and submitting it on Canvas. So if you had an issue with that, just talk to me after class, okay? So I realized that was kind of late last night that I told you that. Hopefully most of you got that, but if there was an issue, don't hesitate. Just talk to me, we'll make arrangements, okay? No problem with that. So let's go over a few of these questions here. Hopefully it helped you to reinforce what we did on Friday. What are we doing? We are doing a crash course review of this part of calculus, right? We said that calculus is basically about two things. You know how much of a quantity you have at every moment, and you want to know how fast it's changing at every moment, right? And then the flip side of that, the rest of calculus, so to speak, is this one. You know how fast the quantity is changing at every moment. You want to know how much of it you have at every moment, right? And we said most of Calc 2 is about this problem, this endeavor. So we said for the first week, let's do a crash course review of that what you did in Calc 1. Okay? So we had this example. The soldier is lowering the American flag, 0.75 meters per second. And we said that was what? The constant rate of change. What was the constant rate of change? What was that?
Negative 0.75.
Negative 0.75 units
Per second.
meters per second. Okay? And so we said, we kind of talked about a good broad meaning of that, not a narrow meaning. So maybe before class, your answer would have been, so what's the meaning of this rate of change? That every second the flag comes down 0.75 meters. Right? Is that true? If there's a constant rate of change of negative 0.75, every second the flag comes down negative 0.75 meters. But then we said, you know a lot more than that though, right?
Every second after they start lowering the flag.
Okay, so you know a lot more than that. What's a better, broader meaning than just you know what happens every second?
For every change in time,
Yeah.
the change in height is negative 0.75 times that.
Right, so for any change in time, we call time x, right? Given any change in time. So do you know how far it comes down in half a second? Yeah. Do you know how far it comes down in 2 seconds? Yeah. You know how far it comes down in 10 seconds? You know all those things. You don't only know what happens in a second, you know what happens in any change of time. So given any change of time or variation in time, what we said, the corresponding change in height, how much it comes down, right, is what?
Negative 0.75 dn.
I was in a hurry this morning, so I'm a little shaky. Sorry. All right. So we said this, dy equals mdx. That frames the meaning of this constant rate of change a lot better than just every second it comes down negative 0.75, because we can say in any amount of time, right? In any amount of time, we know how far it comes down. Negative 0.75 times as much as, right? Because in 10 seconds, how far does it come down in 10 seconds? 7.5 meters, right? We know that. Okay. So that was kind of one of probably the major point of the first lecture, right? And we said this right here is the core principle behind what? This endeavor that we're on. This is kind of the heartbeat of this right here. You know how fast it's changing in every moment is what?
Negative 0.75.
The negative 0.75. You want to know how much of it you have at every moment is? Well, it's almost this, right? So by finding changes in the height, we can easily construct the height, right? How much of it we have. Okay. So then we came to this. So where did this, our net accumulation function come from? Well, this was, right? The values of this function are changes in height. So this was just the same thing, right? This was the dy equals m dx. But this particular accumulation function was what? Since time 0.6 seconds, right? So this is what this function will give. So the meaning of this function, it's going to give, dependent variable is, what? Changes in height since 0.6 seconds for any time since the flag was started to lower, right? For any, that's the independent variable. Any time since the flag was started to be lowered, this function will give changes in height since 0.6 seconds. And it comes right from that dy equals m dx. Okay, so now at the end of class, we had those graphs. And I asked you to find the meanings of these points. What did we say? We said graphs are those lines. You look at those, what do you think? When you look at those, what are you looking at? Remember what we said? When you look at those lines, any line, any graph, any curve, any line, we want to get the mindset that we're looking at what? Points. We're looking at a zillion points, right? Each one of those points showing a correspondence of two quantities that are changing together, right? So this point right here is showing some correspondence of what quantities? The time since we started lowering and the rate of change. So that point is 1, negative 0.75, and it means that what? At 1 second? Good. The meaning of that point is that at 1 second, the flag is being lowered at a rate of negative 0.75 meters per second. Same with this one. This is at, what, 2.3 seconds? At 2.3 seconds, the flag is being lowered at a rate of negative 0.75 seconds. Okay, so now these points, this looks like, what, 0.8 and? Is that negative
0.2.
0.2?
Yeah.
Let's see, no, that's 2/10. So that would be negative 0.15. Is that right? That's what we want instead, right? Okay, so what does that point mean? What does that point mean, the point 0.8, negative 0.15? Somebody knew. Yeah.
At 0.8 seconds, the flag has raised a total of negative 0.15 meters.
Raised?
Negative.
Oh, okay, good. So you said at 0.8 seconds, the flag is raised negative 0.15 seconds or lowered positive 0.15 seconds. Okay, there's another missing piece to that. Yeah?
It's been lowered 0.15 meters since 0.6.
Right, so you just had to have that one little more part. So these values that this function is giving us are changes in height since the 0.6 second mark, right? That was that function that we came up with. So yeah, at 0.8 seconds, you guys put it together. At 0.8 seconds, the flag has gone down 0.15 meters since 0.6 seconds. And so this was our principle number 2, net accumulation function, right? Okay, so that's a little review of the homework just to get us started. Any questions before we move on? Okay? Here we go. All right, so those are principles 0, 1, and 2. Here's principle 3. Principle 3 is changing rate of change. Changing rate of change. And if you can, gave you the in-class worksheets. You can fill those in. I think it's going to be, will give you a better reproduction than your own notes. All right, so we got the same initial scenario, but now here's the rate of change function. Rather than the negative 0.75 constant, here's the rate of change function. So my first question is, why might this be a more realistic rate of change function for the scenario, for lowering the American flag? All right, meet the person next to you if you haven't. Take 30 seconds and answer that question. Why might this be a better rate of change function than the constant rate of change?
that? I'm from this physics area.
Okay, what do we think? Somebody new. Somebody new. Yes, sir.
So we know it's always negative, but it's zero, so it's like it's buoyant,
Yeah?
it's stopping, it's buoyant, and stopping.
Right. So most of the time it's that negative 0.75. That's when it's cruising down. But what's happening on these spikes?
There's usually a gap between when he pulls with one hand and the other.
Yeah. So like when he's changing hands, the flag's going to slow down maybe, and then I'll actually pause for a second, and then start back up again. Right. So these spikes could be like when the soldier's changing hands. Okay. More realistic? It'd be really tough for a person to get a perfectly constant rate, right? I mean, someone maybe practicing a long time could do really well, but this seems a little more realistic, okay? All right, so now I want you to, based on this, okay, so now, based on this rate of change, can we sketch just a general sketch, right? So this is not precise. It's just what would the now with the net accumulation function starting from 0.6 seconds look like for this rate of change? Okay, so 0.6 seconds is right here. So how would it be different, right? We saw what it was before with constant rate. How would it be different now? We're getting a general idea, just a sketch. So it's going to have the same general downward trend, right? Changes are going to be increasingly negative, but what's going to be different? What's that? It's going to curve? It's going to be straight the whole way? Yeah? Right. So what happens on these spikes when the rate of change kind of goes to zero?
The graph becomes...
Yeah, it's going to flatten out each time there's a spike, right? So if you do something like this, then that's the idea here. Okay, so now we're getting into a harder problem, right? So this is harder. Why? Okay, because we have a changing rate of change. Okay, so again, you know how fast the quantity is changing every moment? That means you have the rate of change, or the rate of change function, right? You're given the rate of change function. You want to know how much of it you have at every moment. Where's that? Well, that's almost this, right? So given a profile or a record of the changes in height, it's like you're one easy step away from the actual height, right? So that's essentially finding a net accumulation function is just one small step away from finding the height, which is how much of it you have at every moment. Okay? And so this is our approximate net accumulation function. But how are we going to write that when the rate of change is changing? Right? This is a much harder question than the one we did first class when we had a constant rate of change. Constant rate of change, we've got dy equals mdx, smooth sailing, right? How in the world are we going to come up with this function now with this complicated changing rate function? Okay? All right, so some of you have an idea. Yeah, some of you have an idea. So let's see what... So what we want to do that is we want to leverage what we did in class 1. We want to leverage this dy equals mdx, but what does that require? What is that based on, the dy equals mdx? Constant rate of change, right? So we want to leverage that because it makes the mathematics easy. Somehow we want to leverage that with a changing rate of change. Okay, so here's what we're going to do. So this is page 2 already? Yeah, so flip the page on your sheet. So here it is. What we're going to do is we're going to use delta x, so fixed intervals of time of 0.35 seconds. And in each one of those intervals, we want to leverage constant rate of change. So what we're going to do is we're going to try to estimate what's happening in that interval with one constant rate. Okay, so in this first interval, what would be a good estimate for one? There's the first interval starting at 0.6. What would be a good estimate for the constant rate in the first interval? This is a real easy one. Negative 0.75. It's pretty much the whole time. It's negative 0.75. So here's what you want to draw on your graph. In that first interval, I'm going to say, we'll put one constant rate that's trying to be like the rate in that interval. Okay? Next interval. Oh, this is harder, right? So it starts at negative 0.75 up to 0, almost back down to negative 7.5. So if we had one rate, we only got to choose one rate that simulated or pretended to be that, what would we choose? Something, and we all might choose something slightly different. What about 0? Is that a good choice?
Yeah. No.
To try to reproduce, to try to kind of pretend what the rate is in that interval. 0? No. What about negative 0.75? No. So what would be good? It's heading up to 0 and back down to negative 0.75.
Negative 0.5.
Yeah, so something in the middle, right? Something, it's like you're kind of trying to average it out, right? So something in the middle. So I chose negative 0.4. Maybe you chose negative 0.5. Maybe you chose negative, half of negative 0.75. Was that 0.375? So there's no like right answer here, but there are wrong answers. You don't want to put 0. You don't want to put negative 0.75. Those would not be good. Okay, the next one. What about the next one? Negative 0.75 again, right? Do you see that in that interval, it's pretty much like negative 0.75? Okay, next interval. Now here it starts negative 0.75 for a while, then heads up to 0. So what do we think? Do we want to do negative 0.4 again? Lower or more negative or less negative? Less negative? More negative, right? Because you've got this part at the beginning that's kind of like, you've got this part that's going to pull the average down. So it's like all the values in between, which is about negative 0.375. But then you have these values that we're going to pull the average down. So for this one, I put negative 0.5. Again, you might have negative 0.6, and that would be okay. We're just eyeballing. Okay, next interval is kind of the same thing, but we got even more negative 0.75. Do you see that? It hits all the values from 0 to negative 0.75, but even more. So what do you think here? Negative 0.6 is what I said. Okay, the next one is like the mirror image of that previous one. So I chose negative 0.6 again. And then the next one's the mirror image of the negative 0.5. So I chose negative 0.5 again. And then the last one is back down to negative 0.75 for the whole interval. Okay, so what are we trying to do? So we're like trying to simulate this changing rate of change function with constant rates. And when you do that on big intervals, it's not great, right? But it's the best we can do, right? So it's the best we can do is just try to pick the best thing we have. Okay, so if we have this beautiful, accurate changing rate of change function, why did we just hack it apart and make it really bad, right? So now this red function is trying to be like that. It's not doing a great job. It's the best we could do, but it's not doing a great job. We just made it very inaccurate. Why did we do that? Help us how? Right, so our goal is net accumulation, and what do we have? Constant rate of change, we can get dy's, we can get little changes, right? So we're leveraging constant rates, so we can use dy equals mdx to build, right, the net accumulation function of height, okay? So so this is principle 4. Pretend rate function. Pretend rate function. What? It's trying to be like the real rate function, but with constant rates. Any questions? Anybody have a question? Yes, please. So the red, so this is the pretend rate function, right? So we're trying to build accumulation of height, right? We're trying to get like a height function. And we know we can do that with constant rate of change, the dy equals mdx, right? Because m is a constant rate of change. But as soon as the rate is changing like this, it's all for as x changes, the rate's changing, we can't use dy equals mdx. So I'm making a new function that's trying to be like the real one, that we can leverage the dy equals mdx. We can use that to build net accumulation. Is it better? Okay.
So I have trouble understanding why you made them. So why you made those marks at different levels? So 0.4, then 0.5, then 0.6, then 0.5 again. All negatives.
We have in each interval we only have one rate to pick to try to match the blue graph, right? So
Yeah.
for instance, in here the blue graph is always down there at negative 0.75, so
Yeah.
we'll use negative 0.75. But here it starts at 0 or starts at negative 0.75, goes up to 0 and back down to almost to negative 0.75 again. So if you were to pick one rate that tries to mimic that or simulate that, what would you pick? You wouldn't pick 0. You wouldn't pick 0.
Yeah.
You wouldn't pick negative 0.75. But it's kind of like, it starts up and goes back down, so you pick something in the middle.
All right. I didn't realize that you were using those lines.
Yeah, I'm looking at the rate function, the blue rate function. Now, like this one here, it hits all the rates from 0 to negative 0.75, but then spends a lot of time at negative 0.75. So our guess will be lower,
Okay.
closer to negative 0.75.
Thank you.
Is it better?
Yeah.
Okay. Yeah, ask questions if you guys are not following. All right. So here I give you this table. Time elapsed. And those time elapsed, those are at the endpoints of each interval. 0.6, 0.95, 1.3, 1.65. And then we're gonna build this table. And what's the goal? The goal is to build, we're gonna build the approximate net accumulation function. So that's the point of this table, is to build this column over here, which will be like net accumulation function. So we're going to do the approximate rate of change, approximate change in height, and then approximate net accumulation of height. So before you jump into the numbers, right, our goal is always to understand things first. So you're going to have a conversation with the person next to you. Why are the columns in the table staggered and offset in a way? Why does it make sense that the table looks like this with those middle columns offset? Okay, you talk about that. All right. What? No, not yet. Okay. Not yet. Let me talk through. Hold on. And then what key concept allows? Hold on, guys. Hold on. What key concept allows computing the approximate change of height in each interval? So, what is the key concept that's going to allow us to find these values in column 3? Okay, that's question 2. And then once you're good on those 1 and 2, you really understand that. Now you're ready to start computing. Okay, but make sure you understand questions 1 and 2 before you start jumping into numbers and formulas. Okay, so here's the deal. I'm going to take attendance while you're working on this. Here we go. So why are the columns staggered and offset the way they are? Yes, sir.
Because the thing that we're measuring is the delta x, so it's the change in time.
Okay.
To find our rate of change, we need to put in between those two numbers.
Okay, so he said the rate of change it would be like in between these two, right? The constant rate of change is for the whole interval from 0.6 to 0.95, right? Okay, so that would be the same for all these. What about the third column? Somebody else. Why is the third column also offset? Yeah.
You're using your dy equals x.
Right? And so what's the connection then? Why would it not be like associated with one of these but in the middle? Over that interval. Yeah, what were you going to say?
Yeah. I was going to say that as well.
Yeah, so the change, we were talking about variations, right? Variation is over an interval, right? So this is going to be our variation in height from 0.6 to 0.95. Okay, but now the net accumulation then is back. Oh, sorry, that was not what I wanted to do. I wanted to do this. Now, why is the approximate net accumulation then? Why are those both back aligned with the first column? Why does that make sense? Yeah.
Because it's how much change in height you have accumulated at that particular time. It's not happening over an interval.
Yeah, really well said. Did you hear that? So these now will be how much, so accumulation, right? It builds up over time, right? It builds up over time. So this will be what, say this one here. It'll be the accumulation, all the accumulation you've had so far at that moment. At that moment, 2.35. So the way the table is staggered, make sense? Doesn't make sense. Cool. All right. So then, we got our approximate rates, and those were we already did that. So for the column 2, you just filled it in, right? You just filled those in, so I'll put those in there. Welcome. Negative 0.4. Negative 0.75. He had a big bag of nuts, so he had to leave. Negative 0.5. Nut-free zone, remember? Negative 0.6, negative 0.6, negative 0.5, negative, is this, we got that right? Okay, so now, what key concept allows us to fill in the approximate change in height? What key concept allows us to fill in the approximate change in height?
Take our accumulation function and fill in each rate for each time.
But we're building the accumulation function. We don't have the accumulation function. What did you mean when you said take the accumulation function? What did you mean by that?
The AH is equal to.
No,
I
so
plugged in.
oh, that was for the constant rate of change,
But you
always.
just do it for each interval.
Okay.
And change the rate for each. So instead of doing negative 0.75 for each, I just did it for every single one that was different.
Okay.
And then time elapses each interval in between. So the parentheses.
All right.
Instead of x minus 0.6, it's for each elapsed time.
Okay, cool. Very good. And so in a broad sense, where did that function come from, right? Where did that function come from? That so she was saying she used this idea that we came up from before. Oh. But instead of 0.6, it's going to be what? The starting value of the interval each time. Yeah, that's great. Where did this function come from? MDX, right? MDX. But yeah, what you did was, that's great. That's awesome. Okay? So MDX, so we're going to use the rate, the constant rate in that interval. And then what is our dx? First it's 0.35, then what is it? 0.35, then we fixed the delta x, right? The delta x we fixed at 0.35, and that's what, in this context, that's what our dx is. So you're going to just take each one of those and do what? Multiply by the change in time, and we get these little changes in height in each interval. Okay? And so I'm not going to, we'll see those in a second. Well, let's just write in the first couple here. What was the first change in height in the first 0.35? Yeah. A question, hold on, question.
The likelihood of that is that 0.35 every time, or like the x minus.
No, so that this would be the starting point. So this x would be these starting points of each interval. So the first one would be x minus 0.6. But then it also, so this will always be the 0.35. You should have gotten that thing was always 0.35, right? So yeah, so that thing in the parentheses. Because it'll be, you'll do 0.95 minus 0.6, and then 1.3 minus 0.95. But you didn't need to do this. This was just the way that she thought of it, and that was fine. If you just went straight to this, that's great. Okay, so let's just write down the first 4 or 5 here. What's the first one? 0, 2, or 2? 2, 6, 2, 5. Okay, and then the next little change in height. 1, 4? Next one? Same again. Oh, the first one, same as the first one. Okay, sorry. All right, and then this one is? 7.5. And one more. 2.1. How'd I do? Okay, so we know our rate in each interval. That's what we did when we did the graph. And then we've got these little changes in each interval. We just take the rate times the change in time, right? So now, how do we build the net accumulation of height? So at 0.6 seconds, our change in height was 0. So then at 0.95, how much change in height have we seen? Yeah. Okay, and how do you know that? Yeah, we found that little change in height, right? If we start at 0 and we change by this much, then that's how much we had. That's how much change we had. Or that's how much accumulated change we have so far. So now at 1.3 seconds, we want the accumulated change at 1.3 seconds. Somebody knew. How am I going to get that? Yes, ma'am?
Negative 0.425, just add negative 0.14 to the first one, because it's
Right. So we've got this much accumulated change, and now in the next 0.35 seconds, we've got a little bit more accumulated change. So then altogether, your net approximation will be what we had before, plus a little more accumulation. So what was that value again?
Negative 0.4025.
Okay, somebody new. How do I, so now I want the net accumulation at 1.65 seconds. I want to figure out how much net accumulation of height I have at 1.65 seconds. Again, since 0.6 seconds. Somebody new. Yeah. Negative what?
0.665.
And how did you get that?
Adding on the change in the interval of 0.165 to 0.1.
Right. So you had all the change from before, and now we have a little bit more change in this in the third interval, and we add it on. So look, we know how fast something is changing at every moment. That's like which column in this table? We know how fast something is changing at every moment. Which column is that like? I have column 1 and column 2. Column 2. Column 2 is we know how fast something is changing at every moment. And we want to know how much we have at every moment. Column, someone said 4. Agree? We want to know how much of it we have at every moment. 4, right? This is telling us how much accumulated change in height we have at these different time intervals, right? So we're like building the machinery of this function, this net accumulation function. So check your values. Are we in agreement here? Okay, so remember, any questions? So again, so this is, functions have an independent and dependent variable. In this case, our independent variable is time elapsed, first column. Dependent variable is net accumulation of height. Okay, so before we go on to principle 5, I want to open up GC and do a little bit of work on that question.
I was just going to ask on the last column, I was actually thinking about the height, changing height, which is all positive, so I decided all positive values.
You see why it should be negative? Okay, you're good? Okay, cool. Any other questions about this? All right, I'm going to just talk about GC a little bit. You all should have it working on your laptop. You don't have to get it out. If you have it handy, you can. You don't have to, but you can. So when you open it up, so some of you have already done this. Oh, let's see. You guys are all on Tuesday? So you haven't done this. So in recitation, tomorrow you'll dive into this a lot deeper, but I just want to start you off here. All right, so the first thing is, there's kind of basically two kinds of things. You've got math lines where you enter mathematical statements, and you have text lines. Whenever you want a new math line, you hit Control, Enter, and it gives you a new math line. The math lines have these red or these different colored boxes next to them. If you do Control T, then you can just type text, and it doesn't affect anything. It's helpful to organize and know what you're doing. Okay. So, and then I can start a new math line after that. Okay, so text lines are totally optional. They're just for your own organization and clarity. Okay, so in a math line, I can define a function. All right, so let's go back and define the net accumulation function for the constant rate of negative 0.75. What was that? So I can do. It was a sub h. All right, and when you want to do a function, so like when you can use parentheses for multiplication, like 5. And if I do shift 9, it'll give me both parentheses. And if I put 3, then it tells me that 5 times 3 is 15. And you can make it all kinds of elaborate expressions to solve things. But if I want to do function notation, I don't want to do shift 9 because then it'll think that I'm taking some value AH and multiplying it. All right? So when you're setting up function notation, you want to do control 9. So you'll notice that the parentheses are closer then 5 times 3. And so that's showing you that we're setting up what we call function notation. We're going to practice that this week in recitation, tomorrow and Thursday. Tomorrow. Okay, so what was our net accumulation function for the constant rate of negative 0.75? It was negative 0.75 times x minus 0. So that was your homework, right? That was the one for your homework. Okay, and so when I hit enter or start a new math line, does anything graph? Nothing graphs. Why not? Why didn't it graph this function for us? Well, because a graph is only one aspect of a function, right? So if we have a function, we can do lots of things with it. So this is just defining that relationship. It's not intrinsically the graph. A graph is just one representation, a very important one, but not the only representation and not the only thing that has to do with functions. So if I wanted to graph that, GC, in order to prompt it to graph, uses the variables y and x, just like we're familiar with. So whenever you write a statement, say if I said y equals, now if I want to graph that function, what do I want the y values to be? What do I want the y values to be? I want them to be a sub h of x. And this is the key point here that we're going to be hammering all semester. That function notation, hear me well, function notation gives values of the dependent variable of a function. The output. It gives values of the dependent variable, right? That represents what? The value of this function a sub h when the independent variable has a value of x. Okay? So on a graph, we normally put the dependent variable on the y-axis. So I'm going to set all those dependent variable values to the y values for all the x values. And now when I hit return, it gives me that. Now, what do we want? We only want it for, so I can restrict the domain to x greater than 0.6. And now we've got that same graph that we came up with last class and you had in your homework, right?
How do you do the subscripting?
Control L. Control L. Okay, now I want to highlight, we highlighted a couple points. To highlight a point, Control 2, and so you don't have to memorize this now, you're going to learn all this, but Control 2 will bring up what's called like a point vector. And so if I want, say, 1.6, what is the value of this function at 1.6 so I can highlight the right point? What's the value of this function at 1.6? Negative 0.75, right? So if and let's make that blue so it shows up better. So if you click on those boxes, you can change the color. So now, have I added a point to the graph? No, what did I do? Just highlighted a point that was already there, right? Okay, well that's fine and good, but what about this? What if I want the point at, here, this is a really big point here, don't tune out on me. What if I want the point at 1.827? What's the net accumulation there? How about that? What's the net accumulation 1.8? Can you do that in your head? No. But we have this function defined. It gives us all the points. So I'm going to leverage that function. How can I leverage that function to quickly graph this point? We're going to be doing this all semester. Function notation gives values of the dependent variable for a given value of the independent variable. So important, okay? So I'm going to do a sub h of what? 1.827. Okay? So first and foremost, that notation is not telling you to do something. First and foremost, it stands for something. It just means that value. Now, we can go in and plug it in and find the value. That's fine. But first and foremost, by itself, it's fine. It's complete. It doesn't need to be calculated. Now, if I hit graph, there it is. Function notation, guys. We're going to talk about it tomorrow. Super important this semester.